Hi there! Did you know that high mass stars are rare because they do not form easily, are short-lived and die very young? In this last video on the series of evolution of stars, we'll continue with our discussion on the demise of high mass stars. Let's begin. As we discussed in the previous video, once all the hydrogen is used up in a sun-like stars, it turns into an AGB and moves up the giant branch on the HR diagram. A more massive star, on the other hand, will become a supergiant. High-mass stars consume their core hydrogen very quickly and therefore survive on the main sequence for a few million years rather than billions of years. Once their fuel is used up, the core contracts due to gravity and heats up again. This triggers helium burning in the core. But unlike lower mass stars, this helium fusion via the triple alpha process starts gradually rather than in a helium flash. In moving off the main sequence, the effective temperature of the star drops as its outer layers expand. The decrease in temperature balances the increased radius so that the overall luminosity remains essentially constant. Evolutionary tracks for these massive stars therefore move horizontally across the supergiant region of the HR diagram. The energy liberated by the fusion of helium in the core raises the temperature of the surrounding hydrogen shell so that it too begins to fuse. The size of these supergiants is enormous. Betelgeuse is a red supergiant. It is thought to be between 13 to 17 solar masses and is so large that its outer envelope would extend beyond the orbit of Jupiter if it replaced our Sun at the center of the solar system. Its angular size is so large that unlike other stars, it can be directly imaged by the Hubble Space Telescope. In stars of 5 solar masses or higher, radiation pressure rather than gas pressure is the dominant force in withstanding collapse. The mass is so large that the gravity acting on the core after helium burning is sufficient to produce temperatures of 300 million Kelvin, where carbon begins to fuse with helium to produce oxygen. A star of 8 solar masses or more can go on to synthesize even heavier elements in its core. Gravitational core contraction after all the core helium is used up generates a temperature of about 500 million Kelvin, at which point carbon nuclei fuse together to produce sodium, neon, and magnesium. Production of magnesium releases a gamma photon, that of sodium releases a proton, and neon produces a helium nucleus. Once all the core carbon is consumed, further collapse pushes temperatures to about a billion Kelvin or higher. At these temperatures, many other reactions are initiated and eventually elements such as chromium, manganese, iron, cobalt, and nickel may be produced. Ultimately, the silicon in the core is converted into iron with final core temperatures reaching about 7 billion Kelvin. The core region of a supergiant therefore resembles the layers of an onion with a dense iron core surrounded by shells of silicon and sulfur, oxygen and carbon, helium, and an outer shell of hydrogen. Nucleosynthesis of elements above helium is less efficient so that each successive reaction produces less energy per unit mass of fuel. This implies that the reaction occurs at greater rates so that radiation pressure balances the gravity. While a massive star may spend a few million years on the main sequence, its helium core burning phase may be a few 100,000 years. The carbon burning phase lasts a few hundred years, neon burning phase a year, oxygen burning half a year, and the silicon burning only a day. These massive stars evolve extremely rapidly once they move off the main sequence. Statistically, they are very low in numbers as they are less likely to form than lower mass stars, and their lifetimes are much shorter as well. So in a nutshell, this means that massive stars live fast, die young, and as you'll see shortly, go out with a bang. In February 1987, a new star appeared in the Large Magellanic Cloud, a neighboring galaxy 170,000 light-years away from the Milky Way. What was remarkable was that this was the first naked-eye supernova visible since 1604. The object, now named Supernova 1987A, was a massive star ripping itself apart in a violent event that released as much energy for a short period of time as the rest of the galaxy combined. Supernova 1987A was a Type II supernova. These are massive stars, typically about 20 solar masses or higher, that explode, reaching luminosities of about 1 billion times the solar luminosity at maximum brightness for a few days before fading over several weeks. Identified by the presence of hydrogen lines in their spectra, type 2 supernova are thought to be due to the core collapse in massive stars. Sanderlic, the blue star which exploded as supernova 1987A, is believed to be as massive as 18 solar masses. As discussed in our earlier video, the distinction between different types of supernovae was originally based on their spectral properties. But observations have now established that type 1a supernovae are intrinsically different from type 2 supernovae, which are associated with young stellar populations and are therefore found in the arms of spiral galaxies. Typical rates of explosion of type 2 supernovae suggest that one should be visible in a galaxy every 25 to 50 years. The latest one observed in the Milky Way was detected in the year 2008 and is believed to have exploded 140 years ago. But none has been visible to the naked eye since Kepler's supernova of 1604. Find out more about supernovae in our earlier videos, the links for which are provided in the description below. Extensive observations of supernova 1987A at all wavelengths has helped astronomers better understand the death of massive stars and throw light on how material is dispersed through the interstellar medium in such cosmic explosions. In the last stages of a supergiant, when the core temperature reaches 10 billion Kelvin, iron can photodisintegrate, which means it gets broken by the energy of photons. This process releases gamma-ray photons, protons, and helium nuclei. As iron is energetically the most stable nucleus, such reactions absorb rather than release energy, and so the outward pressure drops. The core therefore contracts further at speeds reaching tens of thousands of kilometers per second. The degenerate core electrons eventually have sufficient energy to react with the protons released by photodisintegration. The reaction between an electron and a proton releases a neutron and an electron neutrino. All the electrons in the core are used up in this process. Since there is no more electron degeneracy pressure, the core continues to collapse. Once the temperature of the core reaches 100 billion Kelvin, the neutrons become degenerate. Neutron degeneracy pressure actually stops the inward collapse of the core. The surrounding material continues to collapse and eventually slams against the now solid, rigid core and rebounds. This forms a massive shock wave which was recently observed by the James Webb Space Telescope. As an analogy, imagine what would happen when a ball hits a wall. It bounces back, right? In the collapsing massive star, the energy involved is vastly greater than that carried by a ball hitting the wall. A total of 10 to the power 46 joules of energy is released in a matter of a few seconds. This is more than 50 times the amount of energy the Sun will produce in 10 billion years on the main sequence. Most of this energy is actually in the form of neutrinos, and only 1% is in the form of visible light. But even that 1% is sufficient for its luminosity to increase by a factor of 100 million, outshining the rest of the stars in a galaxy combined together for a few days or weeks. Although neutrinos usually do not interact with normal matter, the extreme density of the collapsing material and the high flux of neutrinos means that they, together with the shock wave, exert extreme pressure on the material collapsing on the core and blow it off into space at speeds of about 5,000 kilometers per second. The Kamiokande 2, a neutrino observatory buried deep below a mountain in Japan, detected 12 neutrinos in February 1987 from supernova 1987A. This was the first definitive detection of neutrinos from an event associated with a star other than our Sun. These neutrons are also responsible for producing the heaviest nuclei such as lead, gold, and uranium. The high flux of neutrons produced during the destruction of iron is captured by many of the heavy nuclei to produce other nuclei in a method known as the R process, where R stands for rapid. The high number of neutrons available in these few seconds can be captured by unstable nuclei before they have had a chance to decay. In this way, nuclei of elements such as lead and gold all the way up to uranium can be synthesized. The destructive demise of massive stars not only creates new elements but provides the mechanisms by which they are dispersed into space as well. The material ejected from a supernova comprises hydrogen, helium, and other elements synthesized in the star. Massive stars eject much of their material prior to the final explosion. This previously ejected material, together with the interstellar medium, is then hit by a shock wave from the final explosion and the material ejected during it, forming a supernova remnant. The final explosion may propel matter at speeds of millions of kilometers per hour. When this material hits the earlier cloud, it compresses it and heats up to 1,000,000 Kelvin due to the conversion of kinetic energy. At this temperature, the supernova remnant emits radiation at many wavebands. Supernovae remnants expand into space and may extend over tens of parsecs before they disperse into the interstellar medium, normally within 100,000 years or less. While the total amount of mass released into the interstellar medium by a supernova may only be several solar masses, the ejected matter is rich in heavy elements. This material can thus seed the interstellar medium so that subsequent generations of star will have higher metallicities than the original star that exploded. The shock front from a supernova may provide the trigger for subsequent star formation in a molecular cloud. Optically, supernova remnants often have a greenish color indicating the presence of oxygen ions. A massive star undergoing core collapse produces a type II supernova. But what happens to the core material that is not ejected? Well, that depends on its mass. If the mass of the core is less than about 3 solar masses, core collapse is halted by the degeneracy pressure of the neutrons. This results in the formation of one of the most intriguing objects in the universe, a neutron star. Neutron stars are composed of degenerate neutron matter with a density similar to an atomic nuclei, which is around 10 to the power 17 kg per meter cube. This means that 2 to 5 grams of this material, that is just about a spoonful, has a mass of almost 1,000,000,000 tons. Neutron stars range in mass from a lower value equal to the Chandrasekhar limit of 1.4 solar masses up to about 3 solar masses. This upper limit is not well defined and may be up to 5 solar masses in some models. A neutron star is typically about 10 kilometers across. It is a very exotic object with twice the mass of the Sun packed into a sphere the size of a small city. Due to the conservation of angular momentum, a neutron star spins at a very high rate. Whereas a star such as the Sun rotates on its axis roughly once a month, a neutron star can rotate dozens of hundreds of times a second. This is analogous to an ice skater spinning faster as they draw their arms in close to their body. The high rotational speed means that the surface of neutron stars are traveling at relativistic speeds. The gravitational pull on the material must be enormous to prevent the layers being ripped off. The acceleration due to gravity at the surface of a neutron star is of the order of 10 to the power 12 meter per second square compared with just 10 meters per second square at the surface of the Earth. Being so small, neutron stars are also very faint. There is no more fusion taking place in their core, so they can only radiate away stored heat slowly due to their small surface area. Only a few isolated neutron stars have been observed directly. However, there is one type of neutron stars that have been extensively observed from Earth. These are pulsars. Pulsar stands for pulsating radio source. A pulsar produces two powerful beams of radiation which arises due to the intense magnetic field of about 100 million Tesla possessed by neutron stars. The axis of rotation of the pulsar is not aligned with the magnetic poles, just as our geographical and magnetic north poles are different on Earth. As it rapidly spins, one of the radiation beams may cut across the Earth's line of sight. A few pulsars have been observed at visible gamma ray and X-ray wavebands, but the vast majority of around 3,400 currently known have been discovered by radio telescopes. Pulsars have very precise rotation rates which can be accurately measured. They are in fact more precise than the best hydrogen maser clocks on the Earth. Given their extreme gravitational fields and high rates of spin, they provide a useful test of general relativity. Some pulsars have been found in binary systems with other types of stars. Some supernovae remnants, such as M1, the Crab Nebula, are powered by radiation emitted due to a pulsar embedded within it. They are therefore continuously re-energized by the synchrotron radiation emitted by high-energy electrons as they spiral around within the intense magnetic field of the pulsar. Such supernova remnants glow. So far, we have seen what happens to stellar remnants of about 3 solar masses or less. Remnants less than 1.4 solar masses become white dwarfs and will eventually cool down to black spheres of electron degenerate matter. Cores with masses between 1.4 and 3 solar masses become neutron stars, 10-kilometer spheres of rapidly spinning neutron degenerate matter. Young neutron stars may also be detected as pulsars if one of their beams crosses the Earth. Sometimes, though, a star is so massive that the mass of the material left after all the mass loss process exceeds the limit that even neutron degeneracy pressure can withstand. At this stage, the material keeps collapsing inwards until all the mass becomes concentrated at a single point, a singularity. It then becomes a black hole. Black holes are even more exotic objects than neutron stars. With all the mass concentrated at a point, they have extremely high gravitational fields. They are referred to as black because not even light can escape from them once it has crossed a region called its event horizon. At the event horizon, the escape velocity equals the speed of light. Black holes are therefore hard to observe because they do not emit light at any waveband. Rather than looking for a black hole itself, astronomers infer their presence due to their effect on the surrounding matter and more recently by observing their event horizon itself. A black hole that is one component of a binary system may draw material off its nearby giant companion. As this falls towards the black hole, it forms an accretion disk. The material in the accretion disk gets heated and becomes ionized. Charged objects that are accelerated by the centripetal force emit high-frequency synchrotron radiation. This is observed at ultraviolet, X-ray, and gamma-ray wavebands. Black holes formed from core collapse of massive stars in hypernovae, which are slightly more energetic cousins of supernovae, are thought to range in mass from about 3 to 15 solar masses. They are commonly referred to as stellar black holes in order to distinguish them from supermassive black holes present at the center of galaxies such as our own. These may range in mass from about 1 million to 1 billion solar masses. Such supermassive black holes are likely to be responsible for phenomena such as active galactic nuclei and Seyfert galaxies as we discussed in earlier videos. So to summarize, a low-mass star turns into a red giant followed by an explosive demise as a planetary nebula and ultimately into a white dwarf star which continues to fade away for billions of years. On the other hand, a high-mass star becomes a giant or a supergiant star prior to exploding as a supernova. If the inert core left behind is 1.4 to 3 solar masses, it turns into a neutron star, some of which are detected as pulsars. If the leftover core is more massive than 3 solar masses, it will end up as a stellar black hole. This brings us to the end of this series on the evolution of stars. Do comment and tell me how you like this effort, and please do share and subscribe our content with other astronomy enthusiasts. I'll see you next week. Until then, take care.